Hello, welcome to the course SJPHY1C01. The contents of today's lecture is taken from Heat and Thermodynamics by Brijlal and Subramaniam. We will continue to discuss topics from Module 3, Thermodynamics. During the formulation of second law of thermodynamics, Rudolf Clausius felt that the thermodynamic variables pressure, volume and temperature, these are not sufficient to completely describe the state of a thermodynamic system. So he added one more extra variable known as entropy, denoted by letter S. He also made the following important observations regarding entropy. First one, entropy is an extensive property. It depends on the amount of matter in a system, just like mass or volume. You add more matter into the system, the mass increases, or you increase the matter in the system, the volume increases. So these are extensive property. On the other hand, if you look at the density, which is mass by volume, when you increase matter, mass increases, volume also increases proportionally. So mass by volume, density remains a constant. So density doesn't depend on the amount of matter in the system. So such properties are known as intensive property. So here entropy depends on the amount of matter in the system. Second one, Clausius observed that entropy remains a constant during an adiabatic process, just like temperature remains a constant during isothermal process. So based on this observation, Clausius defined entropy as the thermal property of a system which remains a constant during an adiabatic process. Third one, just like internal energy, entropy is also a state function, which means entropy change is determined completely by the initial state and final state. It doesn't depend on the path through which the change happens. If you look at a thermodynamic system, there are two types of states. One is known as the macro state and the other one is the micro state. So if you take a system which is characterized by a particular pressure, volume and temperature, so this is the macro state. And when you look at the molecules inside, for example, if you focus on two molecules x1, x2, x1 has a velocity v1, x2 has a velocity v2. Okay. Now in the next instant, if you look at the same system, pressure, volume, temperature did not change, but if you look at the two molecules x1 and x2, their velocities got interchanged. Now x1 has velocity v2, x1 has velocity v1. So this particular combination x1 v1 x2 v2, I can call it as one microstate, and the second one x2 v1 and x1 v2, this combination I call as second microstate. In both cases the macrostate remains the same. Or taking another analogy, imagine that you are a class of 50 students, the first year BSc Physics student, you are 50 of you sitting inside a particular classroom. Okay. During the first hour, you will be sitting in a particular manner, and in the second hour, some of you have changed your position, so your seating arrangement slightly changed. But in both cases, you are still a class of 50 students sitting inside the same classroom, right? So here in the first hour, I can say that your sitting arrangement corresponds to one particular microstate, and in the second hour, since some of you have changed your positions, the microstate changes to another one, right? But in both the cases, your number is same and you are sitting in the same classroom. In other words, your macrostate remained the same, but your microstates change. So typically, you can have a large number of microstates corresponding to one single macrostate, and oftentimes the microstates are quite random. It's difficult to predict the microstates. And entropy, being microscopic in origin, is determined by the number of random microstates. So it depends heavily on the amount of additional information needed to specify the exact microscopic condition or microstate of the system for a given macroscopic specification or for a given macrostate. So the more details you provide regarding the microstate, or more the number of microstate you identify, more accurately you can specify the value of entropy. That's why often entropy is called as the degree of randomness or disorder in a system. In other words, entropy is a measure of lack of information about the order in a system. Now, if you take dq as the amount of heat exchanged during a particular thermodynamic process at temperature T, then the change in entropy ds during that process is given by ds equal to dq by T. Very soon we are going to see the derivation of these formulas. For now, just take the final result. Okay. Next is change in entropy. Okay. So let's take an example process. So the process is indicated in this PV diagram. You have a number of isothermal processes happening: process AB, process DC, process FE. These three are isothermal processes happening at temperature T1, T2, T3. Then you also have two adiabatic processes, process L and process M. These two are the adiabatic process. Okay. Now, if you look at the combination A, B, C, D, so I have two isothermal processes and two adiabatic processes. This corresponds to one Carnot cycle. Right? Same way, if you look at D, C, E, F, this corresponds to another Carnot cycle. And Carnot cycle is a reversible cycle. Okay. So let's see what is the entropy change during this Carnot cycle. So let's first take the case of cycle A, B, C, D. Here, as the diagram indicates, Q1 heat energy is absorbed from the source at temperature T1, and Q2 is rejected to the sink at temperature T2. And we know how to calculate the efficiency. Efficiency is nothing but work done divided by heat absorbed. This is Q1 minus Q2 divided by Q1, which is also equal to T1 minus T2 divided by T1. Okay. So when you compare these two, you can write 1 minus Q2 by Q1 equal to 1 minus T2 by T1. One factor is common on either side. Cancel that. You get Q2 by Q1 equal to T2 by T1. Or when you interchange the diagonal terms, you get Q2 by T2 equal to Q1 by T1. Moving over to the next Carnot cycle DCEF. So here the heat energy Q2 is absorbed from the source at temperature T2, and heat energy Q3 is rejected to the sink at temperature T3. So efficiency is Q2 minus Q3 by Q2, which is equal to T2 minus T3 by T2. So if you follow the same procedure as before, you will get Q2 by T2 equal to Q3 by T3. When you compare these two equations, you get Q1 by T1 equal to Q2 by T2 equal to Q3 by T3. So this is a constant. So in general, if Q is the amount of heat exchanged at temperature T in going from one adiabatic to another, then Q by T remains a constant. Imagine that these two adiabatics are very close, L and M. These two curves are very close, then the heat exchange between them is going to be very, very small. So you call that small amount of heat as dq, and heat exchange happens at a temperature T. Then from our analysis, we know that the ratio dq by T is going to be a constant. And this constant ratio is called change in entropy between the states represented by the two adiabatics. So putting this result into mathematical terms, you get change in entropy ds equal to dq divided by T. Now, if you have a system which undergoes a finite reversible change from state A to state B, then the total change in entropy you can calculate as follows. Remember, entropy is a state function. So the total change in entropy depends only on the endpoint. So I can write change in entropy equal to SB, the final entropy, minus SA, which is the initial entropy. This is going to be integral A to B ds, and when you substitute for ds, you get integral A to B dq by d. So basically you choose a small section, very small section, call it as ds. So calculate the change in entropy in that small section, then you integrate from the initial point to the final point, then you get the total entropy change. What is the physical meaning of entropy? Unfortunately, there is nothing physical to represent entropy. One can only measure its effects. Now, if you look at this equation, ds equal to dq by t, or you can write dq equal to tds. So heat has the same dimension as the product of temperature and entropy, right? So thus you can conclude that entropy is related to the flow of heat. That's why sometimes people call entropy as thermal inertia. So just as mass serves as a measure of inertia in linear motion, entropy serves as a measure of inertia during heat flow. So you know what is inertia, right? Inertia is resistance to change. So if a particle has lower mass, it's easy to change its motion, or it's easy to change its state of rest. On the other hand, when mass increases, it's difficult to change its motion. So mass acts as a inertia in the case of linear motion. Same way, entropy acts as inertia in the case of heat flow. So if you look at the equation for entropy change, ds equal to dq by t, so here you can easily make out what is the physical implication of this. Suppose you are providing heat energy to a system. We know that by sign convention, when you provide heat energy to a system, it is given a positive sign because the system is gaining energy. So you have plus dq by t, which means your entropy is increasing. On the other hand, if you release heat energy from a system, then dq is going to be negative. Consequently, the entropy decreases. Okay. Now you can understand what's the meaning of thermal inertia. So if the system has higher entropy, it takes you more effort to pass heat energy to a system. So that's why we say it acts as a measure of inertia, just like mass acts as a measure of inertia in the case of linear motion. Now let's try to find out what is the entropy change during various thermodynamic processes. Let's start with the simplest one, which is the adiabatic process. We know the definition of an adiabatic process, right? During adiabatic process, the heat exchange is zero, so I can say dq equal to 0. So straight away I can write ds equal to dq by dt equal to 0. So entropy change during an adiabatic process is 0, or entropy remains a constant during adiabatic processes. That's why we call adiabatic processes as isoentropic processes. Next is a reversible process. So let's take the Carnot cycle because that is the easiest one to understand. So imagine you have a Carnot cycle A, B, C, D depicted in this PV diagram. So it has two isothermals AB at T1 and CD at T2. Then you have two adiabatics BC and DA. So BC changes from temperature T1 to T2 and DA changes from T2 to T1. As we already know, Carnot cycle consists of four processes: isothermal expansion AB, isothermal adiabatic expansion BC, then isothermal compression CD, and finally adiabatic compression DA. So let's try to calculate what is the entropy change during each of these processes. First, isothermal expansion AB. So here you can see heat energy Q1 is absorbed from the source at temperature T1. So remember, we are calculating entropy of the working substance. So here working substance gain heat energy from the source, which means the entropy is a positive entropy, or entropy of the working substance is going to increase. Now how do you calculate the total entropy change? This is going to be integral from A to B ds. So remember the definition of entropy change. This is dq divided by T. dq is the heat exchange. Here heat exchange is the heat absorbed from the source, which is Q1. Since it is heat absorbed, it is going to be positive Q1. So total entropy change is positive Q1 divided by T1. Second one is adiabatic expansion BC. This is straightforward. We know that in the case of any adiabatic process, whether it is expansion or compression, the entropy change is going to be 0. So straight away you can write integral B to C ds equal to 0. Third one is isothermal compression. Sorry for the typo here. This should have been compression. Okay, so isothermal compression CD. So here you know Q2 is the heat rejected to the sink T2. So the working substance is losing heat. In other words, its entropy is going to decrease, or if this is a negative entropy. So what is the total entropy change? Integral C to D ds. This is equal to minus Q2 divided by T2. And finally, you have adiabatic compression dA. Once again, during this process, entropy change equal to 0. Now, what is the total entropy change? The total entropy change is going to be closed integral ds. So, closed integral means you are taking integral over a closed loop. So, here A, B, C, D, A. This is a closed loop, right? So, that's what mathematically represented here. Closed integral ds is going to be integral over AB plus integral over BC plus integral over CD plus integral over DA. And substitute for each of these integrals. So you have closed integral ds equal to Q1 by T1 minus Q2 by T2. But we already know that in the case of a reversible Carnot cycle, Q by T is a constant. So Q1 by T1 equal to Q2 by T2. So if you substitute this result into the previous equation, you get closed integral ds equal to 0. So in the case of a cyclic reversible process, the entropy change is constant, or in other words, entropy change is 0, or entropy remains a constant. This is known as Clausius theorem. So this is the mathematical explanation for the second law of thermodynamics. Now, before winding up, let's do a quick problem. Calculate the change in entropy when 10 grams of ice at 0 degrees Celsius is converted into water at the same temperature. Given the latent heat of ice equal to 80 calories per gram. So first thing, write down all the given parameters in appropriate units. So we are given, the temperature is given because we know that ice gets converted into water at 0 degrees Celsius. So temperature T equal to 0 degrees Celsius. Since we are talking about absolute temperature converted into Kelvin, this becomes 273 Kelvin. Now write down the equation for entropy change, ds equal to dq by T. Now we need to calculate dq. What is the heat energy exchange during this process? Now what is the meaning of latent heat? Latent heat is the heat energy absorbed or released during a constant temperature process like the phase transition. So when water gets converted from ice to its liquid state, basically a phase transition is happening. From solid state, it becomes a liquid state, right? So if you look at the phase transition graph, so on the x-axis you have energy input, or you can simply take it as heat, and on the y-axis you have temperature. Okay. So suppose you have a piece of ice at minus 10 degrees Celsius. You supply heat to it, slowly its temperature increases, finally it reaches 0 degrees Celsius. Now what happens? The ice slowly started getting converted into water, right? Now during this process, when you increase heat energy, the temperature is not going to increase. Instead, the heat energy is used to change the phase from solid state to liquid state. Once the entire solid is converted from the ice state to water state, now when you supply heat energy, the temperature is going to rise again. Finally, when it reaches this point, the vaporization point, what happens? Water slowly gets converted into steam now. So during this point, once again, if you increase heat energy, the temperature is not going to increase. So when all the water is converted into steam, once again the temperature starts to increase. So the amount of heat energy exchange during these two constant temperature phases, this is known as the latent heat. So you have latent heat of ice, similarly you have latent heat of steam. Okay. So we are given latent heat of ice equal to 80 calorie per gram, which means 1 gram of ice, it absorbs 80 calories of heat energy to get converted into water at the same temperature. Okay, so 1 gram absorbs 80 calories. We have 10 grams of ice, so this absorbs 10 into 80, 800 calories. So dQ for this process is 800 calories. So once you identified all the parameters, make the substitution. So ds equal to 800 divided by 273, which is 2.93 calorie per Kelvin. So always remember to write the appropriate units for your final result. So with that we can close today. In the next class we will discuss about entropy change during irreversible processes. Remember, all the natural processes which we see in our world are irreversible processes. So it's very important that we learn how to calculate entropy change during those natural processes. Thank you.